So the next problem is something very similar to a problem which we have already solved. It says that a periodic rectangular pulse is given. So what is a periodic rectangular pulse? A periodic rectangular pulse looks something like this. So let's say the period is capital T. So if the period is capital T, then it repeats exactly after T seconds. So let us say the signal is 1 between plus T by 4 to minus T by 4. Okay, and it is periodic. So this is the rectangular pulse with period that is given to. So in this case, it is said that T, capital T, the period is equal to 1. Now the question is, find out the Fourier series coefficients in two different cases. Case 1, the fundamental frequency is 2 pi. Okay. Now what is the Fourier series coefficient when the fundamental frequency is 2 pi? Let's solve this. So how do you find the Fourier series coefficients? We say that AK is 1 by T integral z of t e power minus j k omega t dt. So for a rectangular function, you have 1 by t integral minus t by 4 to t by 4, 1 e power minus j k omega t. This is something that we already did before. So the rectangular function is 1 in this interval minus t by 4 to plus t by 4, it is 0 everywhere else. So we can just say that this is the integral 1 by t e power minus j k omega t divided by minus j k omega, and the limits are minus t by 4 to plus t by 4. Okay, and what is given here is the omega is given to be 2 pi. So if you substitute 2 pi here, what do you get? So you get it is, and t is given to be 1. So substituting those numbers here, we simply get e power minus j k 2 pi by 4 minus e power minus j k 2 pi by 4. There is a minus here, so it becomes plus minus j k 2 pi. So all we did was just substitute omega is equal to 2 pi and then t is equal to 1. That's all we did. So for t is equal to 1, what is the actual fundamental frequency that we have here? It is 2 pi by t. So this is the fundamental frequency. Okay. So we are in fact expanding this with the fundamental frequency. So let us see what do we get. So we have e power j k pi by 2 minus e power minus j k pi by 2 divided by 2j into k. So this is nothing but sine k pi by 2 divided by k pi. So when the fundamental frequency is chosen to be 2 pi radians per second, we get that the coefficients are equal to sine k pi by 2 divided by k pi. This we have already solved. Okay. So which means under this, the expansion of the signal, the rectangular pulse, would be summation k is equal to minus infinity to infinity sine k pi by 2 divided by k pi e power j k omega t, and omega here is nothing but 2 pi. So we have 2 pi kt. Okay. So this is the expansion of the signal when the fundamental frequency is chosen to be 2 pi. So how does this look like if you plot it? So if you plot it, we can say that for k is equal to 0, remember we can apply limits and then we will get half for k is equal to 0. So what does k equal to 0 represent? K equal to 0 represents 0 frequency. 0 frequency is nothing but the DC component. So it says the amount of DC component that is present in one period of the signal is half. So as you can see here, in an interval of t by 2 times it is 1 and other times it is 0. So it is 1 for half the amount of time in a period. So that's exactly what we see here. So the average of the DC that is present in the whole period is 1 by 2, and that's exactly what we see here. Okay. What happens when k is equal to 1? When k is equal to 1, you get sine pi by 2 divided by pi, which is 1 by pi. Okay. So for k is equal to 1, you get 1 by pi. For k is equal to minus 1, you get minus 1 by pi, and for k is equal to 2, you get 0. Okay. So this is k is equal to 2, and for k is equal to 3, you get sine 3 pi by 2 by 3 pi, which is minus 1 by 3 pi. Okay. And on this side you get the same thing, minus 1 by 3 pi, and so on. In fact, for every even value of k, you always get 0. This is something that we already saw. So this is how the signal looks like for the fundamental frequency of 2 pi. Now let's compute the Fourier series for case 2. So what is case 2? Case 2 is where we change the frequency to pi radians per second. So what is the Fourier series here? The Fourier series now is z of t equals sigma ak e power j k omega t, which is equal to ak e power j k pi t, because we have changed omega. And how do we compute this ak? The ak is now integral over one period, z of t e power minus j k pi t dt. The question is, what should be this t now? So remember, what was our original signal? The original signal that was given to us is the rectangular pulse, right? And the period was t is equal to 1. So we had something like this. 0, its period is 1. This is 1 by 2, and this is 1 by 4. This is minus 1 by 4. This is minus 1 by 2. Okay. So the entire signal repeats exactly after 1 second. So this is one cycle of this periodic signal. Okay. So you can just simply copy paste this one cycle indefinitely, and then you'll get the entire periodic signal. But in this case, the frequency was, the fundamental frequency was omega equals 2 pi. And what is the corresponding period? The corresponding period was 2 pi by omega, which is equal to 1. That was the fundamental period of the rectangular pulse that was given to us here. So when you put k equal to 1, you get omega is equal to pi. What is the corresponding period? The corresponding period here is 2 pi divided by pi, which is 2. So this signal, or this phasor, which has a frequency of pi radians per second, has a period 2 which is larger than the fundamental period of the rectangular signal. So if you integrate this with just period 1, then the phasor will not even complete one full cycle, which means the computation will be incorrect. So one thing that you have to always keep in mind is, when you compute this Fourier series representation and these inner products, it is necessary that both the signals, that z of t and the phasor, should complete at least some integral multiples of the fundamental period of each of their periods. So if you have z of t to have some period t and the phasor to have some period t1, then the integration period, let's say t2, should be some integral multiple of both t and t1, where this is not equal to 0 and this is not equal to 0. Only then this computation is correct. Okay. So you have to ensure that both of them are taken into account so that they have completed at least one full cycle. So you have to ensure that this is true. So if this is not true, then you will be computing the projection of one signal onto the other in half a cycle or in some non-integer multiples of a cycle. So when you do this computation, then the computation of the Fourier series coefficients will be incorrect. So if you remember, how did we get the Fourier series? We said that we'll consider one period and everything else repeats after that. But if you take only some non-integer multiple of a period, then things don't exactly repeat after that, right? So the definition of periodicity is that you can copy paste whatever is there in one interval and that repeats continuously. But if you don't take one integer multiple of an interval, like if the interval period of repetition is t, if you don't take 2t, 3t or 4t, then it will not repeat. So if you take, for example, 3t by 2, then whatever you copy after that is not necessarily the repetition of the original period and you will not necessarily get back the same signal. So it is important that the signals that you consider here should complete integral multiples of their fundamental period. So which means what we need to do here is we have to take the interval of integration to be 2 because the phasor now has a larger period. So in this case we have 1 by 2. Remember where this t came from? That t came from the integral of the phasor with itself. So if the phasor integral is over the period 2 seconds, so this capital T is also now. So for things to be clear, maybe we will rename this as T naught so that this T naught corresponds to this omega naught equals pi. This is the case 2. Okay. So this T naught is a new period which is not equal to the fundamental period of the original signal because this omega is not the fundamental frequency of the original signal. So when you do not use the fundamental frequency of the original signal for this Fourier series expansion, you need to change this time interval as well. Okay, now that we are changing this, so now we have to integrate from -1 to +1 because T naught is equal to 2 in this case. Okay, so z of t e power minus j k pi t dt. Now, which means when you integrate from -1 to +1, what we are integrating is we are now integrating this portion of the rectangular signal. Earlier we used only one period, now we are using two periods. So this is the portion over which we are integrating. So if we are integrating that portion, then the signal is 1 from -1 to what is this point? So this point is minus 3 by 4. Okay, and this point is plus 3 by 4. So the signal is 1 from -1 to -3 by 4, and then it becomes 0, and then once again it is 1 for -1 by 4 to +1 by 4, and then it is once again 1 for +3 by 4 to +1. Okay. So in all these cases it is 1, and this is our integral. Okay. So integrating this, what do we get? So we get e power the same thing, e power minus j k pi t divided by minus j k pi. So we have multiple limits now, minus 3 by 4 to -1, 1 by 4, -1 by 4, 3 by 4 and 1. Okay. So what is this? We can pull this 1 by k outside and have 2j here. So let's first substitute this minus 3 by 4 and -1. So substituting that, we get e power j k pi 3 by 4, and there is this minus here which comes here, and this minus 1 is plus e power j k pi, right? And next this interval, which we'll get plus e power j k pi by 4 minus e power minus j k pi by 4, and for 1 and 3 by 4 we'll get plus e power minus j k 3 by 4 minus e power minus j k pi. Okay. So simplifying this, we get 1 by k pi. So this is the same thing that we had earlier, which gives us sine k pi by 4, and 3 by 4 term put together you get minus sine 3k pi by 4. In fact, what we'll have here is minus sine k pi, or we'll have plus sine k pi, which is going to be always 0. So we can safely ignore that. So this is what we get. So let's compute the coefficients now. So what happens when A0 is computed? So that is k equal to 0. So when k is equal to 0, what we have to keep in mind is that we should not ignore the other term that we had here. The other term that we had here is plus sine k pi, right? So this term does not vanish when k is equal to 0. For k not equal to 0, it vanishes. So when k is equal to 0, we have 1 by 4 sine k pi by 4 divided by k pi by 4 minus 3 by 4 sine 3k pi by 4 divided by 3k pi by 4. So all I've done here is just multiply and divide by 1 by 4 for this term, multiply and divide by 3 by 4 for this term, okay, and plus sine k. Now when k tends to 0, ak, what do we have here? In this case, once again apply L'Hopital. If you apply L'Hopital, this term becomes 1, this term becomes 1, and this term also becomes 1. So we have 1 by 4 minus 3 by 4 plus 1, which is equal to half, right? So we get that A naught is equal to half. All right. So when k is equal to 1, obviously this term becomes 0. So this is 0 for k not equal to 0. So when k is equal to 1, we have 1 by pi divided by sine pi by 4, which is 1 by root 2, minus sine 3 pi by 4. So sine 3 pi by 4 is 1 by root 2 as well, which gives us 0. So A1 is 0. So what about A2? So 1 by 2 pi sine 2 pi by 4, which is sine pi by 2, which gives us 1, okay, and sine 3 pi by 2. What is sine 3 pi by 2? Sine 3 pi by 2 is minus 1. So you have minus of minus 1, which is 2. So sine 3 pi by 2 is minus 1. So minus of minus 1 gives us plus 1. This gives us 1 by 2. So in this case, we have A2 to be equal to 1 by pi. Okay, which makes sense because A2 corresponds to k pi, where k is 2 pi. Alright, so k equals 3. What happens when k is equals 3? A3 equals 1 by 3 pi sine 3 pi by 4, first term, which is 1 by root 2 minus sine 9 pi by 4. So sine 9 pi by 4 is what? So you can say this as 8 pi plus pi by 4. So this is 2 pi. This is once again sine pi by 4. So this term is also equal to 0. So A1 is equal to 0. A3 is also equal to 0. Now what about K4? So now this becomes 1 by 4 pi sine pi minus sine 3 pi, which is 0. So A4 is also 0. What is A5? It is 1 by 5 pi sine 5 pi by 4 minus sine 15 pi by 4. So what is this? You can consider this as pi plus pi by 4, and you can consider this part as 16 pi minus pi by 4, which is 4 pi minus pi by 4. So once again, what do we have here? So you get things cancel out, which is equal to 0. So we have A5 also to be equal to 0. And what is the case? So what do we get when k is equal to 6? So when k is equal to 6, we have 1 by 6 pi sine 6 pi by 4 minus sine 18 pi by 4. So what is this? Once again, you can write this as pi plus pi by 2 and 4 pi plus pi by 2. So this entire term now becomes minus 1, which is minus 2. So this entire term is now minus 1 by 3 pi. So we have A6 equal to minus 1 by 3 pi. Okay, so we have all the coefficients that we want. So when k is negative, what happens when k is negative? So this function, this ak, as you can see, is symmetric. So when k negative, sine of some minus theta is equal to minus sine theta. So there is a minus that comes outside, and there is a minus that is here, which get cancelled out. So a of minus k is exactly what we have here. So we have found out both a of k and a of minus k for k equals 0 to 6. So let's plot how this looks like. Okay. So this is k omega. Okay. In other words, when omega equals 0, what do we have when omega equals 0? A0, which gives us half. This is half. Okay. And when omega equals 1, that is k equals 1, we have omega equals pi. That gives us 0. Okay. And omega equals 2 pi. We have k is equal to 2. We have 1 by pi. And when k is equal to 3, we have 3 pi, that is k omega is in this case 3 pi, which is 0. And when k is equal to 4, we have 4 pi, which is also equal to 0, and 5 pi, which is also equal to 0, and 6 pi, we have minus 1 by 3 pi. The same thing gets repeated on the negative side as well. Okay. So this is what we have on the negative side as well. I will just mark things here. Okay. So now we have different set of coefficients. So when we expanded with omega equals 2 pi, we got the set of coefficients to be, for omega equals 2 pi, we had a k to be given by sine k pi by 2 divided by k pi, which meant that for k equals 0, we had half. So for k is equal to 0, we still had the same term. Let's now plot the ak for omega equals 2 pi. So k is equal to 0, we still have half. What happened when k equals 1? So when k equals 1, we had 1 by pi. So because that is sine pi by 2 by pi, which is 1 by pi. When k equals 2, we had 0. When k equals 3, we had minus 1 by 3 pi, because it was sine 3 pi by 2 by 3 pi, which is minus 1 by 3 pi. So this is what we had for omega equals 2 pi. Now if we plot that at k is equal to 0, what is that? It's the same thing. That's good. When k is equal to 1, what is k omega in that case? When k is equal to 1, the k omega was 2 pi. So we have a different scale. So in that case, when k is equal to 1, we got 2 pi, and still we got the same thing, 1 by pi. And when k is equal to 2, what was omega? Omega was 4 pi, and we still got the same thing. And when k is equal to 3, what was k omega? It was 6 pi, and we got minus 1 by 3 pi, same thing. So as you can see here, when we have different frequencies also, it doesn't matter what is the fundamental frequency you've chosen, as long as it is some integral multiple, you will get the same spectrum. The spectrum does not change. The only thing that has now changed is the resolution of the spectrum. Now we are getting only alternate points. So if we had chosen exactly the fundamental frequency, now you get points only which are integral multiple of the fundamental frequency. So when you reduce the fundamental frequency to some other frequency, like when you choose the frequency of expansion to a different frequency that is half of the fundamental frequency, now you get points in between. Of course, they will always be 0. Now if you make omega to be as pi by 2, then you will get one more point in between these 2 points. So now you have only one point. If you make pi by 2 as your fundamental frequency of expansion, then you will get one more point in between, but they will also be 0, because the expansion is always the same. Okay, because this rectangular pulse contains frequency only of, contains complex sinusoids only of this frequency. So no matter with what value of omega you expand, for only those omegas for which you get 2 pi, 0 and 6 pi, there will be a non-zero Fourier series coefficient. Others, it will always be 0. So it doesn't really matter with what omega you expand. You can expand with the fundamental frequency, or you can expand with something else. Only thing is you have to note down while computing this integral that the period should correspondingly change. The spectrum will never change. As you can see here, we changed the fundamental frequency of expansion, but the spectrum never changed. The spectrum is exactly the same, but you got a lot of zeros in the spectrum. So this is an unnecessary extra computation. So that is why in the Fourier series derivation, we saw that to get rid of these unnecessary computations where we anyway get 0, we'll always expand only with the fundamental frequency. So that we'll exactly get the points that are required for us. So keep this in mind. You can expand with any frequency you want as long as in this integral you have proper full cycles included. But when you expand with any frequency other than the fundamental frequency, you will have a lot of zeros introduced in this Fourier series coefficients, but the spectrum will never change. Keep this in mind.